Good day, grade 12 learners. Welcome to today's physical sciences lesson. My name is Thandiwe Uwane. This lesson is brought to you by Gauteng Department of Education in collaboration with Saibono Discovery Center. Today's lesson, we are going to look at chemical equilibrium. You are free to use our WhatsApp number to interact with us, which is 064 748 8913. Now, we are going to look at the chemical equilibrium. As in our previous lesson, we were looking at the rates that affect the chemical reaction. Now, today we are going to look at chemical equilibrium. Now, what is it that we are going to look at as the objectives of the lesson? We are going to explain what is meant by open and closed system, reversible reaction, and chemical equilibrium. And what is nice is that the definition or the law or the principle of chemical equilibrium is provided on our exam guideline as it is this dynamic equilibrium when the rate of forward reaction is equals to the rate of reverse reaction. So it means when a chemical reaction reaches equilibrium, you will have the rate of forward reaction being equals to the rate of reverse reaction. We are also going to look at the factors that influence the position of the chemical equilibrium or the position of equilibrium, which is pressure for only gases, concentration, and temperature. As we are looking at our lesson objectives, we are going to also list factors that influence the value of chemical equilibrium, which is equilibrium constant Kc. And we're going to write the expression for the equilibrium constant having been given the equation for the reaction. We are also going to perform some calculation based on equilibrium constant, which is abbreviated as Kc. We'll also look at and explain the significance of the high or low values of equilibrium constant. We are also going to apply Le Chatelier's principle, and we are also going to state Le Chatelier's principle as part of the topic under chemical equilibrium. So remember, all the definitions or all the principles that we state, they are normally giving us 2 marks. So it is very important that you know all the principles and you know how to state them correctly as indicated or as written from the exam guideline. We are going to also use Le Chatelier's principle to explain the changes in equilibria qualitatively and interpret graphs of equilibrium. Example, the graph of concentration, rate, number of moles, mass, volume, or a mass versus time. And then we are going to explain the use of the rate and equilibrium principle in the Haber process or the contact process. Now, let's look at the 2 definitions. We are saying we are looking at the open and the closed system. Now, we need to know how to define an open system, and also we need to know how to define a closed system. According to our exam guideline, an open system is a state of a system in which a system continuously interacts with its environment. A reactant or product may enter or leave the reaction. So when we're looking at our rates of reactions, we have seen that we're using an open system because in that case, we were able to see gases escaping from the system, showing that the system is not closed, but the system is open. By open is not that the lid is open, but it means the system, it interacts with its environment. So it means energy can be lost, and also some of the content of the reaction can escape the reaction. Most of the time, what it can escape the reaction is the gas. So what we're looking at in our previous lesson, we're looking at open system. However, what is a closed system? It's a system in which it's in the state of being isolated from its surrounding environment. No chemical is allowed to leave or enter the reaction. So it means now when we talk about a closed system, we are talking about a system that will not interact with its environment. It is an isolated system. Now, let's look at the types of reactions. We have two types of reactions that are given for us in order to interact with. We have irreversible reactions and reversible reactions. What we're doing previously, we're looking at reactions that were stopping, that were one of the reactant, if it is a limiting reactant, is used up, the reaction was gonna stop and it was irreversible. But now we are going to look at reversible reaction. Reversible reaction, it means it's a reaction that can reactants can be able to form the product, and products also be able to form what, the reactants. So by saying irreversible, so it means it takes place in only one direction. So if the system is irreversible, it means it will only take place in one direction. However, if the system is reversible, it means the products can change back into the reactants. As I was explaining, that you will find a system whereby the reactants, as they are forming products, the products are also forming the reactants. And we also have two types of the systems, which is referred as homogeneous and heterogeneous. When we refer to a homogeneous system, we refer to a system whereby all phases of the reactants and products are the same. All phases are the same, meaning that you will find that if reactants are gases, products are also that are formed will also be gases. If they are aqueous, the product will also. So how do you identify a homogeneous a system? You only look at the phases that are given as reactants and the products. And then heterogeneous, obviously it means the phases will do what? Will differ. So there will be a different phases. Sometimes in aqueous reacting with a gas to form maybe a solid, or so you just look at the phases of the reactants and the product for you to classify a system as homogeneous or heterogeneous. Now, we said we are also going to look at equilibrium expression. So when you look at equilibrium expression, we are saying chemical equilibrium involves the balancing of two reactions in which are occurring at the same time in opposite direction. So it means when we are looking at the chemical equilibrium, I think this is a little bit misplaced here. When you're looking at the chemical equilibrium, you are looking at two reactions occurring at the same rate, because it means now you'll have a forward reaction, at the same time you'll have a reverse reaction, and both reactions will occur at the same rate. That is why we say the reaction has reached what? Equilibrium. And we know that we are saying it is dynamic equilibrium because the reaction actually doesn't stop. Dynamic means the reaction doesn't stop. So what is going to happen is that when you reach equilibrium, or when the system reaches equilibrium, you will find that both the forward and the reverse reactions are occurring at the same rate. And sometimes you might think that the reaction has stopped. However, the reaction hasn't stopped because the reaction, we refer to it as being dynamic. Now, what is this chemical equilibrium? As I said, that we need to define chemical equilibrium. We can define chemical equilibrium as the rate of forward reaction, which is equals to the rate of reverse reaction. So the word rate is very important as you are defining chemical equilibrium, because that is what we are looking at. Already we have looked at the rate of reaction. So now we are saying now the rate of forward reaction will occur at the same time with the what was going to be at the equal, is going to be equal with the rate of the reverse reaction. So it means we have two reactions, the forward reaction and the reverse reaction, occurring at the same rate. Now, if we are having an example of this, let's look at the example of this system whereby hydrogen gas reacts with an iodide gas to form what? 2 hydrogen iodide. So what is going to happen is that hydrogen gas and iodide vapor are mixed in a closed container, which it means it's going to be a closed system. As the reaction proceeds, the concentration of H2 and I2 will decrease. As we explained even previously, that as the reaction starts to occur, the only thing that you have in your reaction is the reactants, and we expect that the concentration of the reactants will do what? Will decrease as the reaction progresses, and the rate of the forward reaction will definitely decrease. Remember, there are two reactions that are involved. We have a reaction whereby hydrogen and iodide are forming what? Hydrogen iodide. And we also have a situation where by a hydrogen iodide are going back and are forming hydrogen. So remember, there are two reactions that are occurring here, and we need to do the following. We need to identify the reactants of the forward reaction and the reactants of the reverse reaction, the product of the forward reaction and the product of the reverse reaction. Remember, we are saying there are two reactions that are occurring at the same rate. Therefore, it means if you look at hydrogen and iodide, these two, they can be what? We can say they are our forward reactants. They are the reactants of the forward reaction. They are the forward reactant. And then HI is going to be our forward product. Because as these two are reacting, they are going to form what? Hydrogen iodide. So hydrogen and iodide and iodine, they are forward reactants, and hydrogen iodide is our forward product. Then hydrogen iodide is going to be our reverse reactant, because now remember, it is now going to decompose and form what? Hydrogen and iodine. So it means this one is going to be our reverse reactant, and hydrogen and iodine will be our reverse products, because they will be formed as products in terms of the reverse reaction, but they are reactants of the forward reaction. So the concentration of hydrogen iodide will increase, and the rate of the reverse reaction will also increase. After a certain time, the rate of the forward reaction is going to be the same as the rate of the reverse reaction. That's why we said we have reached a chemical equilibrium. So it is very important to understand that these reactions will occur at the same rate, and both of them, they will have reactants and the product. So when you look at the two reactions, you must be able to identify the forward reactants and the forward product, the reverse reactants and the reverse product. So it means now when the reaction starts to occur, we will expect the forward reaction to do what? The forward reaction, the concentration of the forward reactants to decrease, which will also decrease what? The forward reaction. And we expect that the concentration of the reverse reaction will increase, because we expect the concentration of the product to increase until the equilibrium is reached. Now, this is exactly what I was explaining in terms of what will happen immediately when the system starts to occur. So you can see that this is the graph that represents the reactants, and you can see that it is showing reactants doing what? Decreasing. So the concentration of the reactants, or the rate of the reactants, will decrease. At the same time, you can see that now the rate of the reverse reaction is doing what? Is increasing. So because the product are increasing as the reactants are decreasing. This is the same concept that we discussed on our previous lesson, to say when the reaction is occurring, we expect the concentration of the product of the reactants to decrease, and we expect the concentration of the product to increase. And we can see that at the beginning of the reaction, we have zero product. That is why we normally say initially the only thing that you will find in your reaction is only reactants and not product. But now remember, our reaction now will not, the reaction will not stop, but now the reaction will do what? Will reach equilibrium. And we use this horizontal line to indicate equilibrium. It must not be confused with the horizontal line that we discovered when we're doing the rate of reaction, because that horizontal line, in that case, it was referring to the reaction stopping, or the reaction being the limiting reactant being used up and reaction stops. But now our reaction will not stop, but what will happen? Our reaction will reach what? Equilibrium. And when the reaction reach equilibrium, that's where we see that the rate of forward reaction and the rate of reverse reactions are now equal, and we refer to it as being dynamic equilibrium. So this is a graphic representation to show what is exactly happening with the concentration of the reactants and the product as the reaction, okay, and also what will happen with the rate of the reverse and the forward reaction. We have seen that the rate of forward reaction definitely will decrease, but the rate of the reverse reaction will increase. Now, what are the conditions? Because for you to reach equilibrium, there must be conditions that are going to be met in order for equilibrium to be reached. When we were looking at our previous lesson, we can see that we couldn't reach equilibrium. And the reason why we couldn't reach equilibrium is because the conditions didn't allow us to reach equilibrium. So we need to know what makes us to reach equilibrium, or what are the conditions of equilibrium. So for you to reach equilibrium, the reaction must be reversible. By being reversible, it means the products must be able to go back and form reactants as the reactants are forming what? The product. So the first condition is that the reaction must be reversible, and the second condition is that the system must be in a closed system. It must be isolated from its environment. So for you to reach equilibrium, you must have a closed system, and also the reaction must be reversible. Now, when the chemical equilibrium is reached in a closed system, the rate of what reaction and the rate of reverse reaction are now the same, and the concentration of the reactants and the products remain constant. When we say the concentration remain constant, we mean the concentration of the reactants and the product will not change. So that is why during chemical equilibrium we represent it with a horizontal line, because the number of moles or the concentration or the mass of the product and the reactant will remain constant. And then if a reaction reaches equilibrium, you can combine this concentration into an expression known as what? As equilibrium constant, which is the one that I said is represented by what? By a Kc. So we can be able to combine it in order to calculate the profit or the Kc value as we reach what? Equilibrium. So we are going to use an equilibrium expression when we calculate what? Equilibrium constant. So we know that if you are saying we are reaching equilibrium, we expect that the concentration of the reactants and the product must remain constant. When we say they remain constant, we don't say they are the same, but they don't change. So we can express our equilibrium constant as Kc, whereby we can say Kc is equals to the concentration of the products divided by the concentration of the reactants. As we can see that A and B are our reactants, C and D are our products. Therefore, you can see that when you now express this reaction in terms of Kc expression, is going to be the concentration using the square brackets, of course, because we always represent the concentration using a square bracket. So you can see is a concentration of C, and also the number of moles of C becoming our indexes, becoming our exponents, and then the concentration of D and also the number of moles of D becoming our index, divided by, so C and D, remember they are our products, A and B, they are our reactants. So equilibrium constant, we are using square brackets to show the concentration in mole per decimeter cube, and the indices are numbers of in front, which are representing the number of moles of each substance in the chemical equilibrium, and you can see we are using them as our exponent. So when you are gonna be given an equation and they say write a Kc expression, you know which one are your reactants, you know which one are your products. You might not start with a Kc is equals to the concentration of the product of the over the concentration of the reactants, because at that instant you will be knowing what are your product, what are your reactants. Just like the example that is here, if you are having an expression, a reaction or an equilibrium system like this one, where calcium carbonate decomposes to calcium oxide and carbon dioxide, if we need to write the Kc expression, now what is also important is that you must know that the concentration of all solids is 1. Therefore, it means if you are provided solids, normally you will see that because you are going to multiply by 1, it will be seem like as if you have excluded them. But you know that if you have to divide by 1 or 1 divided by something, that 1 must be there. And also the liquids, we are also saying their concentration is also what? Is also 1. So when we have to express this reaction using Kc expression, we know that we are going to say this is our reactant and these two are our product. So you can see that it's going to be our product concentration over our reactant. So therefore, that is why when you look at it, our solid we know is 1. So it's the same as if the concentration of this one is 1 multiplied by the concentration of what? Of carbon dioxide, divide by what? by 1 again, which is the solid. So that is why you will find that the Kc expression is going to be expressed as Kc is equals to the concentration of carbon dioxide. Even here, where we have our hydrochloric acid gas and we have our water as the liquid, and they give us what? A hydronium ion and chloride ion. When you represent Kc, you can see that because water is a liquid, it was also not included as part of our reactants, because you know that is the concentration of our two products, which is a hydronium ion and a chloride ion, divided by the concentration of hydrochloric acid. So this is how we represent equilibrium constant. And what you must also know is that as we are going to calculate equilibrium constant, we must also look at the value that we are going to get of our equilibrium constant. They are saying if the Kc value is greater than 1 or higher, this indicates that forward reaction is favored. So as we are going to calculate equilibrium constant, we are also going to look at whether the forward or the reverse reaction was favored. And the answer that we are going to get as we are calculating Kc will be our indication whether are we favoring the side of the forward reaction or are we favoring the side of the reverse reaction. Whereby now, if we favor forward reaction, it means we favor the side of the forward product. And if we favor the reverse reaction, it means we're favoring the side of the reactants. And if the Kc value is less than 1, it means now the reverse reaction is favored. So the examiner might ask whether is the forward reaction or the reverse reaction being favored as you are calculating what your Kc. Now let's look at this as one of our activity whereby we can see whether we can be able to correctly represent our equilibrium constant. When you look at number 1, we're having nitrogen gas reacting with 3 moles of hydrogen gas, and then we have our reversible arrows to give you 2 moles of ammonia gas. So first of all, you can say that this is our homogeneous reaction. Why homogeneous reaction? Because all the bases of the reactants and the product is the same. They are all gases. Now, the examiner wants us to represent Kc expression using the following. So obviously, what we are going to do, we can see this is our ammonia, is our product, our hydrogen and nitrogen, they are our reactants. Therefore, it means our Kc for reaction 1 will be the concentration of ammonia using square bracket, of course, and then we use 2 as the index, which is going to be our exponent, divide by the concentration of nitrogen, multiply by the concentration of hydrogen, and because hydrogen there is 3 here, then we put it here. Even if you know that is 1 mole of, so even if we put 1 here, it doesn't make any difference because we know that anything to exponent 1 is the same as that thing. So this is going to be our Kc expression for reaction 1. When you look at reaction 2, this is the one that is the same as the one that we did in our previous slide, where we have seen that at the end of the day, the 2 solids will not be part of our Kc because they are solids and their concentration is 1. But when you look at, if we can decide to make this as a reverse and maybe make number 4 as calcium oxide, which is our solid, reacting with what? With carbon dioxide, which is our gas, and then to give us what? Calcium carbonate, which is our solid. Then in this case now, because our calcium carbonate is our solid, then we definitely need to represent it. If we write the Kc, is going to be Kc is going to be 1 divided by the concentration of carbon dioxide. Why 1? Because we know that the concentration of our solid is 1. And we know that if we multiply 1 with carbon dioxide, it will still be carbon dioxide because calcium oxide is our solid also on the side of the reactants. Then this one, you can see also we have our P4 as our solid plus 6 moles of chlorine gas, giving us 4 moles of phosphorus chloride, which is going to be what? Which is going to be remember, this is our reactant and this is one is our product, and our product is already a liquid. So you can see that now, as we know that our liquid is going to be what? Is going to be 1. So it means it's the same as 1 to the exponent 4, which is not going to make any difference. And then divide by chlorine to exponent 6. Therefore, this is the same as 1 over chlorine 6. Then you can express your equilibrium constant. And it's just an easy mark for you to write an expression or Kc expression, because definitely as you are using the correct reactants and the product, you will definitely get a mark for your expression. Now let's look at how do we calculate Kc. As you have seen that we say Kc is equals to the concentration of the reactant of the product divide by the concentration of the reactant. So you can see that here is an example. This is a very simple example just for you to practice on how do you calculate Kc, where you are given the concentration of each and every substance that is reacting in your equation. So you can see that there's carbon dioxide, mixture of carbon dioxide, hydrogen, carbon monoxide, water at the temperature of 100 degrees Celsius is analyzed, and it is found that the concentration of carbon monoxide is 3 mole per decimeter cube, of water is 7.2 mole per decimeter cube, of carbon dioxide is 2.4, and of hydrogen is 4.5. So this is just a straightforward kind of equation where you just practice to use your Kc. Therefore, you can see this is our Kc expression, and we can say we are going to give 1 mark for it. Immediately when you now start substituting your values of your concentration, you no longer include, or you no longer put the brackets. You can either put the round brackets just for the calculation. We are no longer using the square brackets. So you must know that as you know the concentration of that reactant or product, the round brackets must be used instead of the concentration, because at first you're just saying these are the, I'm going to represent the concentration. Immediately when you know the concentration, you remove the square brackets and you use the round brackets. And you can see that as you are going to calculate, the value of your Kc will be 2. So if the value of Kc is 2, already is telling us something about which type of reaction is favored in terms of forward reaction or reverse reaction. We have agreed that in our previous slide that when the Kc value is higher or greater than 1, it means forward reaction is favored. So it means as we're calculating our Kc value here, it means it is telling us that our forward reaction is what is favored. Okay, then let's look at another Kc or equilibrium constant calculation. In this one now, we are saying a mixture of 0.3 mole of hydrogen and 0.2 mole of oxygen is placed in a closed container with a volume of 200 cubic centimeters. The reaction reaches equilibrium at 50 degrees Celsius, and there is 0.1 mole of hydrogen left in the container. Then they say determine the equilibrium constant of the reaction. So we are provided the reaction of hydrogen and oxygen as 2 mole of hydrogen reacts with 1 mole of oxygen to give you 2 moles of water. Remember, this is our equilibrium, so at least here we're supposed to represent it with using what? Reversible arrows to show that we have reached equilibrium and the rate of forward reaction is equal to the rate of reverse reaction. Now we are provided the initial number of moles of our reactants, and we are told that at equilibrium, when the equilibrium is reached, we find that one of the reactant is having 0.1 mole. Now the first thing that we need to do now, we can use a table method in order for it to assist us to find the concentration at equilibrium. Remember, Kc, you can only calculate equilibrium constant if you know the concentration of your product and your reactants at equilibrium, because that is where the concentration of your reactants and your product will remain constant. Therefore, we are going to use a table method in order for us to do this calculation. Okay, so the first thing that you must know what, okay, okay, the first thing that you must know the ratio of your product and the reactants ratio, and then the initial number of moles. So you need to identify the initial number of moles, and then you need to look at the moles used or produced. Remember, your reactants will form products. So your reactants will be used and your product will be produced, will be formed. And then you will look at moles at equilibrium. And lastly, you will look at concentration at equilibrium. It is very important to write all this in full so that the examiner or the person who's marking can know what are you referring to in each and every bullet, because some of the marks are going to be obtained from the table. Therefore, it means you need to label your table correctly so that we know what are you referring to. So in terms of the ratio, we know that we are having three species on for our reaction. We have hydrogen, we have oxygen, we have water. And from the provided reaction, we know that the ratio is 2:1:2. So you're going to represent your ratio as 2:1:2. So we know already the ratio of the reactants and the ratio of the products. And then initial number of moles. Now, we know that as we are going to start the reaction, even from the graph that we have provided, we know that initially you only have the reactants and you don't have a product. So initially we have 0.3 moles of hydrogen and 0.2 moles of oxygen. So initially you will represent is 0, let me just go back, 0.3 and 0.2, okay? 0.3 moles of hydrogen and 0.2 moles of oxygen. How many moles of water do we have initially? Definitely we have what? 0. And then you don't know the number of moles that you are going to use. You don't know the number of moles that you are going to produce, but we are told that at equilibrium, because now we don't know the use or produce moles, but we know the moles at equilibrium. So we are told that at equilibrium we have what? 0.1 moles of what? Of hydrogen. So we are going to go to equilibrium and say, okay, at equilibrium I have what? I have 0.1 mole of what? Of hydrogen. Now, how are we going to find out how many moles of hydrogen were used? Because we can see that now the system reached equilibrium with 0.1 mole of hydrogen. Therefore, it means we're going to say initial number of moles, which is 0.3, is going to subtract 0.1 mole that we found at equilibrium. And you say 0.3 subtract 0.1 is going to be what? 0.2. So already we know the number of moles that were used for what? For hydrogen. Therefore, we are going to use mole ratio here in order to find mole ratio, in order to find the number of moles of oxygen that we use and the number of moles of water that we produce. The ratio is 2:1:2. Therefore, it means definitely for these two, there will be 0.2 and 0.2. And then this is going to be half of the 2, which is going to be what? 0.1. So we are using mole ratio here in order for us to get what? To get the number of moles that we use or produce, because we know the number of moles at equilibrium. Therefore, it means here is going to be what? It's going to be 0.2 subtract 0.1, which is also going to be what? 0.1. And then you started with 0, but you produce 0.2. It means at equilibrium, you're going to have what? 0.2. Now, concentration at equilibrium. we know that concentration is calculated as C is equals to N over V. And from our statement, we were provided the volume as 200 cubic decimeter. And then we know that we are going to take our 200 cubic decimeter and divide by 1,000, and we're going to get 0.2 decimeter cube. So we're going to convert our volume to decimeter cube, because we know that concentration is the units for concentration is moles per decimeter cube, not moles per centimeter cube. Therefore, we know that now we're going to divide everything here by 0.2. Everything by 0.2. And doing this, definitely you will get a mark for dividing by what? By the volume. And then you will get your values at equilibrium, which is going to be 0.1 divided by 0.2, which is going to be 0.5. And then this one is also going to be 0.5. And this one, because it's 0.2 divided by 0.2, is going to be what? Is going to be 1. Therefore, after getting your now your concentration at equilibrium, that's where now you will now go to your Kc expression and say Kc is equals to the concentration of, remember, water, H2O, remember it was squared, divide by the concentration of hydrogen, which is also squared, multiply by the concentration of oxygen, which is not having any index. Therefore, you will now substitute your concentration as you got them on the other one. The concentration of water, I think it was 1 squared, and then this one, it was 0.5 squared multiplied by 0.5. Then after here, you can now use your calculator to get your Kc as your answer. And we don't include the units. So this is one of the calculations where units will not be included as part of our answer. Then after that, you will get your answer as you are calculating your Kc. But what I want to emphasize is that, let me just go back, is that we need to make sure that as we are labeling our table, we label it correctly so that we know what does each a number represent on the table. So you can see here the mole ratio, and then number of moles at the start or initial, number of moles used or produced according to the mole ratio, and then number of moles at equilibrium and concentration at equilibrium, which is the one that we are going to use to calculate our equilibrium constant. If we can look at another example for Kc, because sometimes you might be required to calculate Kc, sometimes you might be required to calculate the number of moles or mass, depending on what information you are provided by the examiner. So here they say, during a research experiment carried out by initially adding 1 mole of oxygen and 1 mole of nitrogen in a decimeter cube of in a closed system or closed container at 300 kelvins, it was found that concentration of nitrogen oxide present in the container at equilibrium. So now we are given the concentration at equilibrium of what? Of nitrogen oxide, which is 0.1 mole. So we are provided with the expression, and we know that if delta H is positive, we know that the reaction is what? Is endothermic. They say calculate the equilibrium constant also for the reaction at this temperature. So we know we are going to use the same method as we used on the first one, where we look at the ratio of nitrogen, oxygen, and nitrogen oxide, which was 1:1:2. Remember, we only get the ratio where we will get the ratio on the reaction itself. You will see how many moles of each are reacting in order to form how many moles of a product. And then initial number of moles were provided: 1 mole of nitrogen and 1 mole of oxygen, and definitely there is 0 moles of nitrogen oxide at the beginning. Then we are told that now, you see, what we are given is the concentration of nitrogen oxide at equilibrium. And we know that if we are given the concentration of nitrogen oxide at equilibrium, we can be able to use the formula C is equals to N over V to find the number of moles of nitrogen oxide, which will be the number of moles at what? At equilibrium. So it means it's going to be 0.2 divided by 2, which is going to be, so we have found the number of moles of this nitrogen oxide at equilibrium. And then if you started with 0 but you end up having 0.2 at equilibrium, it means you have produced 0.2. And then we are going to use our mole ratio here in order to find what? To find the number of moles of the other species, which is going to be, if this is 0.2 and the ratio is 2 is to 1 is to 1, therefore it means each will be 0.1, 0.1. Then you started with 1, but you have used 0.1. It means it's going to be 1 subtract 0.1, which is going to be 0.9. Even here is going to be 0.9. And then after getting your number of moles, now you can find now the concentration of each of the two at equilibrium, because definitely this one was already provided to you as a clue in order to find the other ones. And then after that, you will use the Kc expression, whereby you say the concentration of nitrogen oxide squared is divided by the concentration of nitrogen multiplied by the concentration of oxygen. And we find that this one was 0.1, and then it's going to be squared, because the squared is here, divided by 0.5 multiplied by 0.5, and our Kc value become 0.049, and this one we can see that is less than 1. So we agreed that if the Kc value is less than 1, it is telling us that the reverse reaction is favored. Okay, as I said, that it's not that always you will calculate a Kc. Like in this example, the thermal decomposition of calcium carbonate is an example of a heterogeneous equilibrium. I think we know what we mean by a heterogeneous equilibrium already. You can see here is a solid, here is a solid, but here is a gas. So the phases are not the same. So this is a heterogeneous equilibrium. The decomposition that takes place in a container can be represented by the following reaction. 1 mole of calcium carbonate, which is our solid, give us 1 mole of calcium oxide and 1 mole of carbon dioxide. They say initially 5 grams of calcium carbonate is placed in a closed container of 500 cubic centimeter. We know if we are given cubic centimeters, we definitely need to do what? To divide by 1,000 so that we can find our decimeter cube, which is definitely going to be 0.5 decimeter cube. And then it's heated. Equilibrium is reached at 900 degrees Celsius. Now they say calculate the mass of unreacted calcium carbonate that remains in the container at equilibrium if the Kc. So you see here you are provided with the Kc value. The first thing that you know, if you are provided with the Kc value, already you know that Kc will be equals to, definitely this one is our reactant, so it's going to be divided by 1, and this one is our solid, is not going to be included because its concentration is also 1. Then it means our Kc will be equals to the concentration of what? Of carbon dioxide. And the concentration of the Kc value is provided as 0.0108, which is going to be equals to what? To the concentration of carbon dioxide. So we already know what is the concentration of carbon dioxide. Then we can use the concentration of carbon dioxide to calculate the number of moles of carbon dioxide. So we are going to calculate the number of moles of carbon dioxide, which is going to be 0.0108 multiplied by 0.5. Remember, this is our volume that we are provided of the system. And then we are going to get the number of moles of what? Of carbon dioxide. Under the stoichiometric calculations, we know that we use what we have to get what we don't have. But now, what are we calculating? The examiner wants us to calculate the number of moles, the mass of unreacted calcium carbonate. Then we know that the ratio of the reaction between calcium carbonate and carbon dioxide is 1:1. Therefore, if we know the number of moles of carbon dioxide, we can use the mole ratio to find the number of moles of what? Of calcium carbonate. Therefore, we are saying here the ratio of this one is to this one is 1:1. Therefore, if the number of moles of carbon dioxide is 0.054, it means the number of moles of calcium carbonate is going to be 0.054. Then if we are looking for a mass, we know the number of moles is equals to M over big M, or capital letter M, which is going to be 0.054 equals to M divide by the molar mass of calcium carbonate. Calcium is 40 plus carbon dioxide is 12 plus oxygen is 16 times 3, which is 48. When you add them together, you will find what? 100 grams per mole. Then this is the 100, where the 100 is coming from, which is the molar mass of calcium carbonate. And then we get the mass that didn't react, which, because we get the mass that reacted with what? With to form carbon dioxide. Then the examiner is looking for the mass that didn't react. So if you started with 5, because our question was saying initially we had 5 grams, but we know that only 0.54 reacted, then we are looking for the mass that didn't react, unreacted mass. So it means it's going to be 5, our initial mass, subtract 0.54, the reacted mass, in order for us to get the unreacted mass. So it's going to be 5 minus 0.54, which is going to give us 4.46 grams of what? Of calcium carbonate. So you can see that not always that when we are given a calculation, we need to calculate Kc. Okay, this one we are not going to do, but it's almost the same concept. 1 mole of A, 2 moles of B reacts in a 2 cubic decimeter container if equilibrium is if at equilibrium 0.75 mole of C has been formed. Calculate Kc. So we are going to use, like we did in number 1, we are going to use the table in order for us to be assisted to find the concentration at equilibrium. And already you know that what is the concentration of C at equilibrium, which is our product. So it will assist us in order to use a mole ratio to find to calculate Kc, in order for us to calculate to find the concentration at equilibrium. This is a previous question paper, whereby definitely we need to know how are these questions asked, and definitely if you want to start with chemical equilibrium in your examination, you know that you must go to question number 6, because chemical equilibrium is question number 6, and that's where you'll find chemical equilibrium. Consider the balance equation below of a hypothetical reaction that takes place in a 2 cubic centimeter container at 300 kelvins. We have 2p plus 1q2 gas, giving you 2pq gas. And you can also say that this is homogeneous mixture, because, or homogeneous reaction, because the phases are the same. And then the first thing that the examiner wants you to do is to define chemical equilibrium, which is the rate, is when the rate of what reaction is equal to the rate of reverse reaction. And all of us definitely must get these 2 marks, because it is very easy to define chemical equilibrium. And then the amount of each substance present in the chemical equilibrium mixture is at 300 is shown. So we are shown the moles at equilibrium of each and every species that is on the reaction. P is 0.8, and then Q2 is 0.8 also, and then PQ is 3.2. And then the temperature of the container is now increased to 350. And then when the new equilibrium is established, it's found that 1.2 mole is present in a container. Then they say, is the reaction a positive or negative? So we know that when we look at the reaction, we can see that the reaction is going to be negative, because there will be an, remember, you will use Le Chatelier's principle to explain this. So the reason why I don't want us to go through this, I want us to just look at the calculation, because that is what we're doing at our first equilibrium. We have found that initially at our first equilibrium we have 0.8, 0.8 and 0.2, and we were told that at equilibrium it was found that we were given the value of Q, which is 1, of P, which is 1.2 moles. So because P is 1.2 moles, we use it so that we can find the change, or the number of moles used for P. And then after that, we're going to use the mole ratio in order to find the other number of moles of other species, and then we calculate. We are going to divide by our volume, and we are going to find our concentration at equilibrium, and then we use our Kc expression in order to find what? To find the Kc, which was 10,889. And definitely, as you can see, that how are they making this? For you to identify your initial, you are going to get 1 mark. For you to identify the change, another mark. And also for you to use the mole ratio. This C is for the mole ratio, because remember it was not provided. It's the fourth, what is it? Is the third mark. And then for you to find the other number of moles, the change here is going to be the mark, and dividing by the volume, all the number of moles found at equilibrium dividing by the volume is another mark. So for the table, you can see there are already 5 marks. So that is why it is very important that as you are going to deal with the table, you label it correctly, so that we can be able to get the 5 marks. And then for the Kc calculation is another 3 marks, which will be total of 8 marks. So it doesn't mean that when you are calculating Kc, if your Kc value is incorrect, you are not going to be given some marks. There will be some marks for the skills that you'll be using as you are trying to find the concentration at equilibrium. And also there's a mark which is always there for everyone to get, which is the mark for the Kc expression. So everyone must be able to get a mark for Kc expression. And number 2, everyone must be able to get this mark, which is the number E is represented as number E here, because you are going to take whatever number of moles that you are going to get at equilibrium and divide by the volume, which is the second mark that we must get. And also another mark is the use of mole ratio, which is also very important, because as you are going to use mole ratio, you will be provided, or you will be awarded a mark for a skill of using mole ratio. Okay, before we do this one, I think we need to go to the factors that affect equilibrium. Normally, we are saying the factors that affect equilibrium are represented as CPT, which is going to be like your Cape Town abbreviation. So the factors that affect equilibrium, we can say they are Cape Town. What is the abbreviation standing for? The T is for temperature, the P is for pressure, and the C is for concentration. So equilibrium is affected by pressure, temperature, and concentration. Now let's look at how does each factor affect equilibrium. Let's start with temperature. We are saying an increase in temperature favors endothermic reaction. A decrease in temperature favors exothermic reaction. So when the system has reached equilibrium and you decide to increase the temperature or decrease the temperature, definitely the system will be affected. So we are told what will be favored, what type of reaction will be favored in terms of the increase in temperature and the decrease in temperature. So the rate of both endothermic and exothermic reaction increase with the increase in temperature, but the rate of the endothermic reaction will be faster than the one of the exothermic reaction until another equilibrium is reached. Now we need to know that when you increase temperature of a system, we expect, because temperature was one of the factors that affected the rate of reaction. So as we are going to increase the temperature, we said an increase in temperature will increase the rate of reaction. So that is why both the reverse and the forward reaction will increase when you increase temperature. However, the endothermic reaction will increase more. If your forward reaction is endothermic, then it means your forward reaction will be increasing more than the reverse reaction. But both of them, you must expect them to increase as we are increasing the temperature. Then concentration, an increase in concentration of any of reactants, or a decrease in concentration of any of the product favors forward reaction. So it means if you increase the concentration of one of the reactants, you expect forward reaction to be favored. Or if you decrease the concentration of your product, you expect your forward reaction also to be favored. But the decrease is the opposite. If you decrease the concentration of any of the reactants or an increase in the concentration of any of the product, will favor the reverse reaction. And then in terms of the pressure now, which affects only the gases, we are saying an increase in pressure favors the reaction that produces a least number of moles, or the least amount of what, of a gas. So we are saying here, you are going to look at the number of moles of your forward and your reverse reaction. When you increase pressure, now you're going to check the number, the total number of your moles in both reactions. So the increase in pressure will favor the reaction which is having how many, or the least or the less number of what, of moles, and the decrease in pressure will favor the reaction that produce a larger number of moles, which these are the factors that affect what, equilibrium. So as you can see here, why is the change in pressure affecting the chemical equilibrium? We know that pressure affects only the gases molecules, and from Boyle's law we know that the relationship between what, pressure and volume. So how are we going to increase our pressure and how are we going to decrease our pressure? Definitely volume will be involved, because there's a relationship between pressure and volume. If you increase volume, you definitely know that pressure will decrease, because pressure is inversely proportional to what, to the volume. So the increase in volume will definitely decrease the pressure, and the decrease in volume will increase the pressure. So we are saying an increase in pressure is when you are doing what, when you are decreasing the volume, and that kind of disturbance will favor the reaction with least number of moles. But when you decrease pressure is when you are increasing volume. So we must not be confused and think that in this case we are saying volume is affecting equilibrium. The only way to increase pressure is when you are decreasing the volume, and the only way to increase pressure is when to decrease pressure is when you are increasing the volume. So the increase and the decrease of the volume will definitely affect what, our pressure, because pressure and volume are doing what, are inversely proportional, even when we look at the Boyle's law. So we can see here there is a decrease in volume, so there will be an increase in pressure. If you are increasing volume, there will be a decrease in pressure. Now, when you look at the increase, let's look at this example of our Haber process, which is nitrogen gas reacting with hydrogen gas to give you ammonia. 1 mole of nitrogen reacts with 3 moles of hydrogen to give you 2 moles of ammonia. So already you can check the number of moles, because we are referring to pressure, and pressure is the one that will look at how many moles are in each of the reaction for it to be favored if the pressure increases or decreases. So this side we have 1 plus 3, which is 4 moles, and then this side we have what, 2 moles. So we can see that now the number of our moles in both reactions are not the same. Therefore, they say pressure affects only gases, as you can see. The ratio is 4 molecules of reactant to 2 molecules of what, of a product. An increase in pressure will favor the least number of moles, which is going to be our forward reaction. So the forward reaction will be favored, and the yield or the production of ammonia will do what, will increase. So if you want to produce more of ammonia, what we are going to do, we are going to increase the pressure of the system by decreasing the volume. And we know that the forward reaction will be favored, because that is the reaction with the least number of what, of moles. So but now when you decrease pressure, you expect the system to favor the reaction with a larger number of moles. So obviously the larger number of moles is the number of moles of what, of our reactants. So it means the decrease in pressure will favor the side with greater number of moles, and reverse reaction will be favored, and definitely the yield of ammonia will decrease. So we need to know how we explain in terms of what will happen if you decrease the pressure of the equilibrium or you increase. You firstly talk about which side will be favored in terms of the one with larger or lesser number of moles, and the second bullet, it must say which reaction is favored, and the third bullet, it must talk about what will happen after that effect has been done at equilibrium. So you can see here the yield of ammonia decreases as the reverse reaction is. Remember, ammonia is our forward product, is our forward product. Therefore, if you need more of ammonia, it means you must favor the forward reaction, because that is where ammonia is being produced. So if you are decreasing pressure, you are not going to get as much ammonia as you want, because it means now our reverse product will be the one that will be reverse product will be the one that will be favored. So that is why the decrease in pressure will result in a decrease in the yield of ammonia. We are going to take a 1 minute break so that we can just continue and explain these disturbances at equilibrium, also looking at Le Chatelier's principle. So we are going to just spend 1 minute for that. Welcome back, grade 12s. We were still busy with the disturbances at equilibrium, which I said it's going to be nicely explained using Le Chatelier's principle. So already I have started explaining the issue of the disturbances at equilibrium, which is stated by Le Chatelier's principle. So what does Le Chatelier's principle say in terms of the disturbances at equilibrium? It says when equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that oppose the disturbance. So it means when you have reached equilibrium and you are changing temperature, or you are changing concentration, or you are changing pressure, because those are the three factors that affect equilibrium, it means the system now will oppose that change, definitely by doing what? By favoring the side that will oppose the change. So it means a new equilibrium will be reinstated. But the only way the system to do that is by favoring the reaction that oppose the disturbance. Definitely, I think it's a normal situation whereby if there's a disturbance, you will try by all means to oppose the disturbance, so that you are regaining, or you are reinstating a new equilibrium. So we must know that we might be expected to state Le Chatelier's principle, which is a principle that I have already started explaining in terms of what will happen if you increase pressure. And pressure, already we have seen what will happen if you increase pressure in an equilibrium. We have seen that when you increase pressure, you are going to favor the reaction with less number of moles. When you increase pressure, or when you decrease pressure, you are going to favor the reaction with more number of moles. So we are going to use the Chattelier's principle to explain the changes at equilibrium, and also we are going to use the graphs in order to look at what will happen at equilibrium if there's a change. So let's look at it. So this is the same concept that I was using previously to say we have seen here that now, but you can see now that we are also provided the heat of the reaction. We are also provided the enthalpy of the reaction to say whether the reaction is endothermic or exothermic, which we know that now this will only affect our reaction if we are referring to the factor which is our temperature. But in terms of the pressure, we have already discussed to say what will happen if you increase the pressure and what will happen if you decrease the pressure, which is the example that we just did now. Now, in terms of the temperature, now let's look at the temperature. What will happen when you increase the temperature, and what will happen when you decrease temperature? An increase in temperature will favor the reaction that absorb energy, which is endothermic. So when you are increasing temperature, you will favor endothermic reaction. Now, how do you explain this in terms of the provided reaction. The first thing that you are going to check, you are going to look at the the heat of the reaction. As we can see here, we are told whether our reaction is endothermic or exothermic by using the change in NH. So you can see that our delta H is less than 0. So if delta H is less than 0, it means our reaction is what? Is exothermic. So it means now our reaction is exothermic. If the delta H is greater than 0, we know that our reaction will be endothermic. And this condition, it is the condition of our forward reaction. So we are told here that our forward reaction is exothermic. Now, the first thing that you must ask yourself, what will increase the forward product? So if you are saying the reaction is exothermic, we know that an increase favors endothermic and a decrease in temperature favors exothermic. We can also use a abbreviation like intermendo, the temexo. Increase in temperature favors endothermic reaction. Decrease in temperature favors exothermic reaction. Now, already that we can see that our reaction is exothermic. So it means for us to favor the forward reaction, definitely we must decrease the temperature. We must favor what? We must favor exothermic reaction. If we increase temperature, it means now we are going to favor our reverse reaction. And remember, by the increase in temperature, we agreed that both the reactions will increase. However, the one that is favored will increase even faster than the other one. Their rate of increasing will not be the same. So we need to know what will happen when we increase or we decrease temperature. So an increase in temperature favors endothermic reaction. So when the examiner starts and say the temperature of a system maybe is increased, the first bullet that you must give, you must tell us which reaction is favored by the increase in temperature. So it means you will start by saying an increase in temperature favors endothermic reaction, and you'll get 1 mark for that, because that is another skill that you have accumulated in order for you to know which type of reaction is favored when you increase temperature. Or if the temperature is decreased, you will state to say the decrease in temperature favors what? Exothermic. Now, in terms of the concentration, when you are having a reaction like this one of hydrogen and iodine to give you hydrogen iodide, you can see that hydrogen and iodine will react to give you a iodide. Now, what will happen if you add more hydrogen? If you add more hydrogen, it means you increase the concentration of what? Of hydrogen. When you add hydrogen, the system will decrease the concentration of what? Of the other reactant, which is iodine, in order to increase your product. So it means you are increasing the concentration of hydrogen, the system decreases the concentration of iodine, so that at the end of the day your forward reaction will be favored. So that is why we said when you increase one of the reactants concentration, the forward reaction will be favored. But when you decrease the concentration of a product, you will still favor what? The forward reaction, because the system will oppose the disturbance by favoring the side that will do what? That will reinstate a new equilibrium. So the increase in concentration of the reactant or the decrease in the concentration of a product will both favor the forward reaction. However, if you decrease the concentration of the reactant, definitely the forward reaction, the reverse reaction will be favored. And if you increase the concentration of the product, you are expecting definitely your reverse reaction to be favored, because in that case, remember this now, when you look at the reverse reaction, is our reactant of the reverse. So if you increase the concentration of the reverse reactant, we will expect the reverse reaction to increase, which is, I think, is not confusing, because when we are saying hydrogen iodide, we are saying hydrogen iodide is our reverse reactant, and hydrogen and iodine are our forward reactant. So if we are increasing the concentration of the forward reactant, we expect the forward reaction to be favored. If we are increasing the concentration of the reverse reactant, we expect the reverse reaction to be favored. So you need to know what are you increasing. But what is nice is that you know that the system will decrease the concentration of one of the reactant and also do what? Increase. So if you see in a reaction whereby, especially graphically, where you see one of the reactant increasing and the other one decreasing, and also the product increasing, you will know that in that case you increase the concentration of the reactant of one of the reactant, and the other one will decrease and the product will increase. Now, the effect of a catalyst. When you add a catalyst, there will be no effect. A catalyst does not have any effect at equilibrium. A chemical reaction, because the rate of forward reaction is equal to the rate of reverse reaction, will change with the same amount. So when a catalyst is used, the reaction takes place with a lower activation energy. That is why the rate of forward reaction and reverse reaction will then, so it means the condition of equilibrium will be reached sooner. But you must know that the Kc will not change as you are adding a catalyst, unlike in those reactions that we're doing on our previous lesson, where a catalyst was doing what? Was increasing the rate of reaction. Now let's look at this activity. The following hypothetical reaction reaches equilibrium in a closed system. X2 gas plus Y2 gas give you 2XY gas, and we can see here our heat of reaction is what? Is less than 0. So already we know that this is our exothermic reaction. And if this is an exothermic reaction, we know that the only way to favor the forward reaction, whereby we look at the production of 2xy, we must decrease the temperature. And then we can also look at other factors. If you increase one of the concentration of the reactants, we also expect the forward reaction to increase. Now, which one of the following changes will increase the amount of xy, which is our product? So they're just saying which one will favor, which one of the factors will favor forward reaction. So because we have identified our reaction as exothermic, definitely the decrease in temperature will favor our forward reaction, because our forward reaction is our exothermic reaction. Increase in reaction will favor the reverse reaction, because our reverse reaction is going to be our endothermic reaction. So if we wanted more of the reactants to be formed during equilibrium, we're going to increase temperature so that we favor endothermic reaction and we favor the reverse reaction. It is very important to say reversed instead of reversible, because sometimes you might be confused with the two terms of reversible and reverse. Reversible means forward and backward, but the reverse means only backward. And then an increase in pressure. Yes, we are dealing with gases. However, look at our reaction. Both reactions are having 2 moles each. So the number of moles of each side are equal. Therefore, if the number of moles of each side are equal, then the pressure will not have any effect. So there is no effect. Either you increase pressure or you decrease pressure, because none of the reactions will be favored, as the number of moles are equal in both sides. They are 2. The equation below represents a chemical reaction at equilibrium in a closed system. You can also see here we also have another exothermic reaction, and then we have hydrogen and iodine to give hydrogen. Which one of the following changes will increase the yield of HI? So already we know if it is about temperature, the temperature must decrease, because it's the temexo, because this is it's an exothermic reaction. And then we also know that if it is about pressure, there won't be any effect, because you can see is 2. So pressure will not have any effect. The only thing that can also have an effect is when you increase the concentration of the reactant. So they say, which one of the following will increase the yield of HI? The increase in temperature, definitely not. Remember, the increase in temperature will favor endothermic reaction, and the forward reaction is exothermic. So increase in temperature is incorrect. However, the decrease in temperature definitely is correct, because our forward reaction is exothermic. So the decrease in temperature favors exothermic. Increase in pressure by decreasing the volume, decrease in pressure. So pressure, remember, we have already identified that it doesn't have any effect, because the number of moles of each oxide, the sides are equal. This one actually is the same as the one that we were using, that side, to just calculate Kc. A chemical reaction reaches equilibrium. Which one of the following statement regarding this equilibrium is true? So we know when we are saying the reaction has reached equilibrium, we expect the rate of the forward reaction to be equal to the rate of the reverse reaction. And we also expect that the concentration of the reactants and the product remains constant, because at equilibrium, there won't be any change of the concentration of the or number of moles of reactant or product. Number A says the concentration of individual reactants and products are constant, meaning that they remain the same. Okay, let's look at number 2. The concentration of individual reactants and products are equal. Definitely, this is not true. We know that they must remain constant, which is true when they say it remains the same. The concentration of the individual reactants products are 0. Definitely, this is incorrect. The concentration at equilibrium is not 0. The reactants and the products will definitely have a certain concentration which is more than 0, that will not change. And then the concentration of individual products increase until the reaction stop. Definitely the reaction is dynamic. We know that the reaction is dynamic. It doesn't stop. So to say the reaction stops, it is actually, this is an outlier. It is totally incorrect. This is number D. So the correct answer is the concentration of the individual reactants and products are constant, because we know that at equilibrium, the concentration of the product and the reactants remain constant. Okay, we can, so in summary, we can say, we can talk about the disturbances to say an increase in concentration of the reactants, forward reaction is favored. That one actually we have already said it. Okay, I don't know what happened. Just a little bit. Okay. Okay, let me just fast forward this so that we can go to the slide that we are in. Okay, we are now looking at the summary of all the changes that we have talked about that affects the equilibrium, whereby we said in terms of the concentration, the increase, let me just go to the slide, the increase in the concentration of the reactants, any of the reactants, definitely will expect the forward reaction to be favored. Let me just go to the summary. Let me just had a little bit of a disturbance, but it's not. Okay, here we are. So we are saying an increase in the concentration of any reactants, we expect the forward reaction to be favored. An increase in the concentration of, this one, it is now an increase. Okay, an increase in the concentration of a product. Here, I think we're supposed to say, oh yes, of a product. Yeah. So if you increase the concentration of the product, not the reactant, I think this is incorrect, you expect a reverse reaction to be favored. Why is the reverse reaction being favored when you increase the concentration of the product? Remember, for the reverse reaction, your product is the reactant. So it's the same as when you increase the concentration of the reactant of the forward reaction, because the product at that time will be your reactant instead of being a product. When you decrease the concentration of the reactants, the reverse reaction will be favored. I think we've seen that. And when you decrease the concentration of a product, we expect the forward reaction to be favored, because where we have increased the concentration of a product, a reverse reaction was favored. But when we decrease the concentration of a product, we expect the forward reaction to be favored. So you need to go through these changes and check how are each of them affecting your equilibrium. And the only way for you to understand that, you must ask yourself which one is the forward reactant and which one is the forward a product. And then at the second time, which one is the reverse reactant. So your product will always be your reverse reactant. So whatever that you do to the product, you must just know that it will affect, definitely, is either the forward reaction or the reverse reaction. So when you increase the concentration of your reverse product, of your reverse reactant, definitely will expect the reverse reaction to be favored, because you are increasing the concentration of the reactants that are the reverse reactants. So that's why I'm always saying, check your forward reactants, check your reverse reactants, check your forward product, check your reverse product, so that you can understand, especially when coming to to concentration, what will definitely happen to the system. Then in terms of the temperature, the increase in temperature is favoring what? Endothermic reaction, and the decrease in temperature is favoring exothermic reaction. I think this one we have explained it and we have seen. And then pressure now. When you increase pressure, you will favor the reaction with least number of moles. When you decrease pressure, you will favor the one with more number of moles. And addition of an alkalis of a catalyst will have no effect at equilibrium. Now, let's look at the interpretations of the graphs of equilibrium. Definitely, we started in question number 5, where we look at what will happen to the concentration of the reactants and the products as you start the reaction. We have seen that the concentration of the reactants was decreasing, and we also represented the concentration of the reactants and the product graphical, where we have seen that at the beginning of the reaction, we have seen the concentration of the reactants decreasing and the concentration of the product increasing. Let me say, normally they start from zero, increasing. This is the graph that we're looking at in terms of the concentration of the reactants and the product. And we know that in our case here, because we are dealing with systems that will are in an isolated system and that are reversible, we know that we are going to reach what? Equilibrium. So we are going to look at the rate versus time graph, and also the amount versus time graphs in terms of the number of moles or mass or volume, and the concentration versus time graph. So we are going to look at those graphs in order for us to interpret the disturbance at equilibrium. Now, let's say the equal amount of sulfur dioxide oxygen reacts in a sealed container and reach equilibrium. So now remember, the reaction doesn't come to a stop, but the reaction will reach equilibrium because of the favorable conditions. We are given the heat of the reaction, which is indicating that this is exothermic reaction. So this is very important that you identify your forward reaction as endothermic or exothermic. And then we are given the reaction: 2 moles of sulfur dioxide react with 1 mole of oxygen to give you 2 moles of sulfur dioxide. And then we are going to look at the reaction rate graph. Our forward reaction is indicated by a bolded dark line, and our reverse reaction by a dotted line. And then the concentration of, or the amount of moles, they are represented by this. For the oxygen is the dark line, and then for sulfur dioxide a dotted line, and sulfur dioxide a dash and a dotted line. So we know that these square brackets, they represent what? They represent concentration. Now, when the reaction initially starts, the forward reaction rate is higher because the reactants initially are higher. We expect that. Remember, we were also saying we will look at the gradient of the graph. The gradient of the graph will tell us whether the reaction rate is higher or lower, and we are going to refer to the steepness of the graph. So when you start at the beginning, you can see that the forward reaction, definitely we expect the forward reaction to be a little bit steeper and then becoming less steeper, less steeper, less steeper. So we are saying initially the rate of the forward reaction is higher because we have higher, the concentration of the reactants is still higher. And then the reverse reaction at the start is 0. The rate of reverse reaction is 0 at the start, as there are no products to react in the reverse reaction. That is initially when you start the reaction. Then the concentration of the reactants, which is going to be our sulfur dioxide and oxygen, will decrease, and the concentration of the product is going to be what? So if the concentration of the forward product will do what? Will increase, as the rate of the forward reaction is greater than the rate of the reverse reaction. So the forward reaction rate is gradually decreasing and the reverse reaction is gradually increasing. So this is initially, this is at the beginning initially. So we expect that the rate of the reverse of the forward reaction here, it is decreases, and the rate, because remember we're using the dotted line for the reverse and the solid line for the forward reaction. Also, in terms of the concentration, you can see that the concentration of my two reactants, which is sulfur dioxide and oxygen, is decreasing, and the concentration of sulfur dioxide is increasing. This one is the rate graph, as you can see, and this one is the concentration graph. Remember, the concentration is not the same, but the concentration remain constant. And then here it just indicates the rate of the forward and the reverse reaction. Now, what will happen is that after some time, our the forward reaction will take place at the same time as the reverse reaction. So here you can see the two lines, they meet, they coincide. It means here we have reached what? Equilibrium. So the rate of forward reaction and the rate of reverse reaction at equilibrium is equal. So that is why when you look at the rate graph, you can see that they form one line where they meet to show that they've reached equilibrium. And in terms of the concentration time graph, you can see that the concentration of our reactants and our product remain constant, but you can see that they don't have the same concentration. So the lines on the graph are all horizontal. The concentration are not necessarily equal, but that means the concentration is constant. The concentration doesn't change. So the solid line indicates that the concentration of these substances remain constant, but it's not the same. And the two lines will not meet because they are not equal, because the concentrations are not equal. Now, if you increase the concentration of oxygen, which is one of the reactant, you can see that both the reverse and the forward reaction will increase. But remember, the solid line represents forward reaction. So the forward reaction will increase more and the reverse reaction will increase less, because the forward reaction is favored by increasing the concentration of one of the reactants until a new equilibrium is reached. So this one is from the first equilibrium, and this one is the second equilibrium after the what? After the disturbance. So here what we have done, we have increased the concentration of one of the reactants, and you can see that this one, the forward reaction graph is sharper. It rises sharper because you are increasing what? You are increasing the concentration of one of the reactants. So it means the rate of the forward reaction will be faster than the rate of the reverse reaction. However, both the reactions increases, but they don't increase at the same rate. And then in terms of the concentration graph, so I'm referring to both graphs at the same time with the same changes, so that we can see how are we going to represent, or how is it represented in terms of the change that will occur at equilibrium. So we know that the solid line represents oxygen. So you can see that oxygen, as you increase the concentration, it sharp rises, which this one, it is a graph that represents what? Oxygen. And then we know that as you increase one of the concentration of the reactant, the other reactant concentration will decrease, which is our sulfur dioxide. So when you increase oxygen increase, but sulfur dioxide decrease. as you can see, it decreases, so that our sulfur trioxide, which is this one, increases. This is what we were looking at when we were saying when we increase hydrogen, the iodide concentration will decrease, so that iodine concentration will increase, so that hydrogen iodide concentration will increase. So you can see here, this is the effect of what? Of concentration that being increased at equilibrium. And then after that, a new equilibrium will be established, whereby the concentration of our reactants or our product remain constant again. So let's look at this activity in terms of what we have just explained in terms of the changes at equilibrium. So you can see we have A, B, and C. And then we are given the number of moles of A, B, and C in this vessel. So you can see that as the reaction starts here, when it starts, because maybe it's from another equilibrium, you can see there's a slight decrease, and slight increase of what? Of AB as our product. So they say the graph shows the number of moles of A, B, and AB versus time under the various condition. And then what are the concentration of A, B, and AB at time T20? So T20 is here. So we can just read the concentration because our graph is drawn to scale of each and every reactant and product. So you just look at what is represented. This one is, it represents A. So our A is 0.15 moles. As you can see, is our A. And then our B, the B is represented by this one. Our B is 0.10. Here you are just interpreting the graph. And then our AB, which is this one. Okay, our B is this one. Our B is 0.05. And then our AB is going to be 0.10 mole. So here on our question number 1, it was just to say, how can we interpret the graph? And then how can we be sure that the system has reached equilibrium at T20? You can see that the number of moles of each substance is not changing, is constant. So you can see here that definitely this means that equilibrium is being reached. And then explain the change in concentration at A of A and B at time T25 to T35. So when you look at the concentration here, you can see that there's a sharp increase of B, and A is decreasing and AB is increasing. So it means what happened here is that because there's a sharp increase in the concentration of B, so it means here the concentration of B was increased. And as the concentration of B was increased, the concentration of A will do what? The concentration of A will decrease, and resulting to the concentration of AB being increased. So you just look at the shape of the graph, it will tell you what is happening. If you see an increase, it will also tell you whether it was temperature or it was concentration, looking at what we've been discussing. And then explain the changes of concentration. Okay, so I think we have explained the changes of concentration at at time 25, and then also this one, you can see here that at T1 ammonia is increasing, hydrogen as one of the reactant is decreasing as nitrogen. So you can also tell here that there was an increase in concentration of what? Which one is increasing sharply? Is nitrogen. So there was an increase in concentration of nitrogen as the concentration of hydrogen decreases, and then you reach the first equilibrium. And then in this one, you can see that there's an increase there's an increase in all the graphs, and the increase in all the graphs might be because of the increase in temperature, or might be because of the increase in pressure, depending on whether which side will be favored. And then also here you can see that our equilibrium also remain constant. And then here there's an increase in ammonia, there's a decrease in what is it? There's a decrease in ammonia, there's an increase in nitrogen. And so here I think it might be because of the change in temperature, because it depends whether, remember, this is exothermic reaction. So if it is exothermic reaction, if we see that both both our reactants are increasing and our product is decreasing, so you can see that maybe because our forward reaction is exothermic, then it means here we have increased the temperature. So if you increase the temperature in T3, so T3 means it will have increased the temperature. Then if you have increased the temperature, what is going to happen? When you increase the temperature, increase in temperature favors endothermic reaction, and our reverse reaction is endothermic. Therefore, both the nitrogen and hydrogen will increase. So these are just the graphs that we're going to explain in terms of what will happen at equilibrium if you make one of the changes. As you can also see here, is about the concentration and also the rate. So we are gonna see also that in terms of the catalyst, both the reactions are just increasing, meaning that the equilibrium will be reached sooner. So that is why we said there is no change in the concentration, or there is no effect of the catalyst in terms of the equilibrium, because it will just assist the two reactions to reach equilibrium sooner. Here they are talking about the condition in terms of the yield of this methanol, and you can see that our forward reaction is still exothermic, so we know what is it that will make us to get a high yield of ammonia. In terms of the pressure, you can see that the increase in pressure definitely will favor forward reaction, which is a high yield of this, and then also the decrease in temperature will also favor the high yield of this, because our forward reaction is exothermic. Then in this one, it was about just a Kc expression, being given a Kc expression. So identify which reaction represent our Kc. It cannot be a 1, because our 1, remember, our A is our solid, so it cannot be A. And then also B, A is our liquid, it cannot be B. Let's look at this one. Our A is aqueous, yes. Our B is solid, so it's not part of this one. It's multiplied by 1, yes. Our C is there with 1, and but look at our D, the 2 is here, so it's also incorrect. The correct one, I think, is going to be this one, because we have 2D, which is our index. So we need to be very careful in terms of how do we represent our Kc. And then also here, we have reached equilibrium with these two as it is decomposing. They are saying here the graph represents the decomposition of nitrogen tetroxide in a closed system. So this is the concentration graph. Which one of the following correctly describe what happens at T1? At T1, that's where the system reaches equilibrium. So we are saying we cannot say this one is used up and this one is. The rate of forward reaction equals to the rate of reverse reaction. Yes, is correct. The concentration of the reactants and the products are equal, which is incorrect. The concentration of the reactants and the product are not equal, but they remain the same. And then here we are looking at this X, Y, and Z. So they're saying which one gas X is placed in a container at time T1. From time T1, the gas decomposes to Y and Z. A chemical equilibrium between the three gases is reached at Tx, okay? The following graph, concentration versus time, shows the changes that occur during the reaction. So you can see that at equilibrium, we can be able to read the values of Y is 0.2, of X is 0.1, and of Z is also 0.1. Z is also 0.1. So it means in terms of X and Y, the X, this one is Y. What is this? Yeah, this one is Y, this one is X, and this one is Z. So the ratio of X and Z are the same. So when you look at it, say A is 3X, 2Y, and Z, no. Here is ratio of 1 is to 1 is to 1, which is incorrect. X and Z, yes, they have the same ratio, and then they are the half of Y, which is definitely correct. and this one is incorrect. So here they were just saying, can you use the mole ratio in order to identify your reaction? We have come to the end of our lesson. Thank you so much for watching. Please go back to the video and also try and check whether you can be able to answer the questions on question number 6, where you are going to use the KC calculations and also where you are going to apply Le Chatelier's principle. From my side, thank you so much for watching. Until next time, goodbye.